In these last few examples, we're going to take a look at finding probabilities where we have to kind of be very careful of the wording, and then we're going to be connecting this to tree diagrams in order to help us see what sorts of outcomes satisfy the probability we're looking for. So in this initial example, it says, suppose a family has 3 children, and we're going to determine the number of sample points in the sample space. So that's asking how many outcomes are there in the sample space. So since the family has 3 children, that's going to be a 3-stage experiment. So I'm going to put down 3 blanks, where each of the stage would be the options for the children that they could have at that stage. So for the first stage, or the first child, there are 2 options, either a boy or a girl. For the second stage, a boy or a girl. And for the third stage, a boy or a girl. So we'll multiply those together, and then that gives us that there are 8 outcomes possible in the sample space. Okay, so let's go ahead and draw a tree diagram for this scenario. So from an initial point for the first child, you could either have a boy or a girl. The second child is a boy or a girl. And we're going to assume that boys and girls are equally likely at each stage. Alright, so we'll just finish off these branches for these last ones. Alright, so there are my outcomes. So if we wanted to, you could re-record them at the end of the branches. It's not necessary, but if it just helps you see what's going on. So you could have boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 2 girls, then a boy, and then all 3 girls. Alright, so let's find some probabilities. So for this initial one, determine the probability that none of the children are boys. Alright, so the probability that you have no boys in any of the 3 children. So no boys is the same thing as saying all girls, right? Okay, so if you don't have any boys in any of the 3 children spots, that means all the children are girls. So out of the 8 total outcomes, there's only 1 that have girls for the first, second, and third child. So the probability of no boys is 1/8. Determine the probability of exactly 1 girl. So we'll just write 1 girl. So what this is getting at is it doesn't matter if the girl occurred first, second, or third, but you only want 1 girl in the 3 children. So out of the 8 possible outcomes, how many of them only have exactly 1 girl? Well, you have the boy, boy, girl, you have the boy, girl, boy, and you have the girl, boy, boy options. So there are 3 ways you can have exactly 1 girl out of the 8 possible outcomes in your sample space. For the next one, determine the probability of at least 1 girl. Now there's going to be a handy way that we can approach finding probabilities involving at least once. So the probability that an event occurs at least once, we can find this probability by doing 1 minus the probability that the event does not occur. So let's see why this is going to work. Determine the probability of at least 1 of the children as a girl. So at least 1 means you could have exactly 1, exactly 2, or all 3 of the children could be girls. So all of those would satisfy at least 1 girl. And there's going to be quite a few outcomes that satisfy that, right? The only ones that we don't want to count in this event are going to be ones that don't satisfy at least 1. Another way of saying that is that nobody can be a girl. So that's what this probability is going to be over here, that the event does not occur, that you don't get at least 1, you get none. So for this particular problem, the probability that you have at least 1 girl you can find that by doing 1 minus the probability that you have no girls, that event does not occur at all. What's the probability that you have no girls? Well, no girls is the same thing as saying all boys, right? So what's the probability you're going to have all boys for all 3 children? So out of the 8 outcomes in the sample space, there's only one way that you can have all boys. So if we do this calculation here, 1 minus 1/8 will give us 7/8. And you might have been able to see that that would be our count for our numerator just by analyzing if you have at least one girl. So you would get these 3 that we listed for part C, and then you would have, so let's maybe go through here. So this has at least one girl, that has at least one girl, that has at least one girl, this one does. All of those outcomes have at least one girl. So the only one that we don't want to count is this one. And then that's what this probability over here is taking care for us. It's removing that as a possibility. Let's take a look at finding a probability using the phrase at least in another scenario. So in the next one, the situation is if we assume a stock is equally likely to go up, go down, or stay unchanged, and a broker selects 2 stocks at random from the New York Stock Exchange list, what is the probability at least one of the stocks goes down? So the probability at least one goes down. Now remember, they're going to be selecting 2, so this is going to be a 2-stage experiment. We can do 1 minus the probability that neither go down. Okay, so this one we would count the first one down, but the second one isn't. The first one is not down, but the second one is, or they could both be down. So the only other ones that we don't want to count is neither of the stocks being down. Let's draw a tree diagram to see what's going on in this. So there's going to be 2 stages. On the first stage, or for the first stock, it could either go up, it could be down, or it could stay unchanged. So we're just write S for stay. So maybe we'll put that down here so we can see how we're going to code these. Okay. The second stock could go up, it could go down, or it could stay. There are 3 options that could happen on the first stock, 3 options that could happen on the second stock. So overall there's going to be 3 times 3 or 9 options. I want to find how many of them have neither of them going down. Alright, so in this one, neither of them went down. On this one, neither of them went down. On all of these ones, the first one went down, so I don't want to count any of those. Coming down to this last set of branches, this one, neither of those went down, and this one, neither of those went down. So 4 of them satisfy neither of them going down. So if we do this calculation, we get 1 minus 4/9, or 5/9. And since you have the tree diagram right here, as opposed to doing the subtracting out of who you don't want to count, if you wanted to, you could just approach this by counting how many of them have at least one down. So you could be like, I want to count this one, these 3, and that one, and then you can see that you actually want to count 5. Either approach works. Just trying to show you another example of how this formula applies for getting us the probability that we want.